want to talk about Inventor advanced assembly techniques. So the three topics I guess we'll be covering are related to modifying large assemblies quite quickly. And we'll discuss what the three traditional methods of design are, that being bottom up, middle out, and top down. So my name is Niall Smyth. I'm a senior technical consultant with A2K Technologies. My background is mechanical engineering and design. So I'm interested in simulation, FEA, CFD, and I also work on the data management side of things, so things like vault and so on. So today's agenda, we're just going to give a brief introduction to people, first of all, that aren't familiar with A2K Technologies, about what we do. And before I keep talking, I'll just do a very quick sound check. So if someone could perhaps type into the message box or the question box if the audio is working okay, as I don't want to be talking on and the audio not working correctly. Brilliant. Thank you, Stephen. Cool. So as I said, we'll just do a brief introduction to A2K Technologies, then we'll move on and we'll start talking briefly about the different techniques that are available to you in modeling with Inventor. And then we'll jump into the software, we'll do a demo and a summary of what we've covered. And at the very end, we'll leave time for questions and answers. So if you have any questions along the way, if you'd like to just type in the questions into the question box, and what I will do is we'll go through them one by one at the end of the webcast. Okay, so A2K Technologies. In summary, we're a very large organization. We're Autodesk's largest reseller in Australia and New Zealand. We're a platinum partner, which is the highest tier you can get with Autodesk. And we have a large staff of people who have come from industry mainly. So everyone has experience. They're not just trained in how to use the software, but experience in using the software for commercial purposes. We don't just offer Autodesk technology, so we also offer Adobe, Microsoft. There's very good global e-training, which is a online training solution, which is excellent if people can't make training or can't get time off of work to go training. So it's a step-by-step training program for Inventor, Revit, any of the Autodesk software. In terms of the areas that A2K cover, we obviously sell software. We also do a lot of consulting work, training, and supporting the products we sell, as well as the hardware. So we also supply things like computers, CAD machines, workstations, and we have a very large technical knowledge base as well. And that's based around our blog, different events we host, webinars like this, white papers, and tips and tricks that go out in our monthly newsletter. So our general mission statement, our value proposition, is to work as hard as we can to provide a win for everyone. So a win-win scenario, that is the ability to deliver more, deliver better, and hopefully exceed expectations. So moving on towards the technical side of the presentation, let's give a look at design methodologies and what the traditional Inventor design approach was. So when everyone learns Inventor, they learn how to create a part, they learn how to create another part, and then they join all these parts together in an assembly. And you define constraints between all these parts. So that's the kind of the basic starting point. The issue is when you start working with larger assemblies and when you want to update things, if you update one part, that means you potentially have to update a second or a third part, change the geometry to modify it, and there's a lot of maybe constraints that have to be changed. So it can be a little bit slow, especially if you want quick design changes. And anyone who's involved in design will know design is an iterative approach. So you'd start with something and 3 weeks later you might end up with a completely different design. So the ability to make changes quickly are critical because it's not that hard to do the initial model. It's when you go through each different review. If you have it set up in a way where you have to change 10 different parts each time something changes, and you have to redefine 20 different constraints each time something changes, then that's going to slow you down. And that's where your time towards the end of the project gets longer. So a second approach is, again, most people will have learned this if they've attended Inventor training, is middle-out design. So this is where you start putting your parts together, and then you start modifying or creating parts at the assembly level. So this means you'll have adaptive parts. So one part will be dependent on another part. So the position of a hole might depend on the position of a shoulder in another part. So to use this, you have to use adaptivity. And adaptive parts are parts that update when another part changes. And the adaptive symbol is shown just between those two little first IPT symbols on the left-hand side. So it's that little blue and red arrows. So that's a sign that it's adaptive. And adaptivity is good to use, especially when you're designing things and finalizing your design. But it can be a bit slow, especially if you update parts in the wrong order, and it can get a little confusing. Also, if you have lots and lots of adaptivity in an assembly, it can cause issues. It can slow it down, it can cause crashes. So while it's a good addition, it's still not the fastest way of changing assemblies and modifying assemblies. So that brings us to a third approach, which is top-down design. So in this top-down design scenario, what we do is we start with a part file. And we basically design our entire assembly within that part file, or reference to a part file. And from that single part file, then we create an assembly. Okay? So it'll seem clear once we get into Inventor and once we get started on it. But what you'll see is that the master part is basically the part in the middle. It's the part just under the assembly icon. And what we'll do is that part gets derived into other parts. And deriving a part is something that all of these top-down design techniques have in common. And I'll explain a little bit about that in a second. So when using a top-down design technique, a key thing is to stop at the start of your design and give a think, and build your design intent into that part. So you actually map out how you're going to create your part. You map out what parameters will potentially change. And then that will allow you to use things like skeletal modeling, which is just another name for master sketching. You can also use multi-body modeling, which creates multiple bodies inside in a single part, and then we derive an assembly from that. Or you can use layout design. So there's three top-down design techniques that are commonly used. Layout design is for designing mechanisms. So it's where you want to get the kinematics or the dynamics of a mechanism correct, or the dimensions, at the sketch level. So you can design a big assembly, design how it's going to work at the sketch level, and then create an assembly from it. So moving on to the next slide. I mentioned derived parts, and all the design techniques have derived parts in them that we mentioned above. So what a derived part does is it actually creates a link to another part so that when changes are made in the original file, the derived part updates based on those changes. So for example, if you're building a car and you've got a left-handed wing mirror assembly and you've also got a right-handed mirror assembly, well then you only need to create the left-handed assembly and you can derive a part based on that left-hand assembly, such that if I make any changes to my left-hand assembly, the derived part updates. So I can create a left-hand side and I can derive a right-hand side part. So that's quite useful for multiple things. It's used in designing castings and machined parts as well, where you've got different operations at different stages. For example, if you're machining something, you might want to have a block and then derive a part where your initial machining is done, and then derive another part where your holes are drilled in, and so on. So, as I mentioned, design intent is key for top-down design methods, and we'll look at this as well when we get into the demo. Parameters are very important as well. Well, not very important, but they allow greater efficiencies in design. So if you use parameters and you use them cleverly, you can make changes very quickly. When we get into the demo, and that's just going to be in a second, so we're going to look at naming parameters. And for people who haven't worked with parameters before, if you try naming parameters, there's a couple of rules to follow. So basically, you cannot start with a number. You cannot have a space in the name for the parameter. An Inventor has reserved certain names, such as capital H, lower h, capital V, capital T. When doing top-down design techniques, and to be honest, in general, doing assembly work, you should use the origin work planes as much as possible. The reason is these origin work planes, they never change. They're there, they're locked in space, you can't move them. So if you base your geometry and your positioning of parts off your origin work planes, and your spacing off of origin work planes, then your model is going to be a lot more solid. It reduces the chance of you actually deleting a sketch plane or a face and then causing further downstream features to crash. Another useful tip is naming sketches and work planes for reference. So we'll do that as well when we get into the Inventor environment. So master sketching is the first one we'll look at, which is also referred to as skeletal modeling. Second one we'll look at is solid body modeling. And you'll have noticed if you use Inventor and you haven't used solid bodies a lot, that a lot of the features like extrude, hole, pattern, chamfer, so on, you can apply these to solids. And there's a little button in the dialog box for solids. So and the final one then will be layout design. And this is similar to using sketch blocks in AutoCAD. So in our sketch level, we'll create blocks, and those blocks will then create parts for us. Okay, so let's jump into Inventor. And we'll swap across here. And what I'll do for the master sketching example is I'll start from scratch. And we'll discuss some of the principles of top-down design techniques. So where I'm going to start is I'm going to start on my origin work plane. And I'm going to build an assembly that's going to look like a chute or a kind of a funnel for maybe materials processing or whatever. So I'm going to start by creating a rectangle. And you'll notice that I've got direct input switched on. Okay? So I could type in my dimensions as I go, but just to explain exactly what I'm doing, I'll go right-click and say General Dimension. And as I'm putting in my dimension, what I'm going to do is I'm going to give it a name. So I'm going to call this Outlet Width equals, and maybe make it just 500 mil. And my next dimension then will be my outlet depth equals maybe 750. Okay, and I'll just constrain that sketch very quickly and easily, and my sketch is fully constrained. So finishing that sketch, what I could do here is rename my sketch. Okay, as best practices say, we should name our sketches and name our planes. So I could call this inlet dimensions, or inlet sketch. Sorry, outlet, excuse me. Outlet sketch. And by naming my parameters, what that actually does is it allows me use my parameter editor. You can see here that the two parameters, when I go to my parameter editor, which is the quick FX button up in the quick access toolbar, you can see that I've got outlet width and outlet depth. So as I name my parameters, they go into my parameter table, which allows me to make changes later on very quickly. If I'm not sure what dimension I've called what parameter name, I can right click and I can say dimension display, and I can say show me instead of the name, or instead of the value, let's show the name, and it tells us exactly what each dimension has been named. So I'll right click again, dimension display, go back to value, and finish that sketch. So next thing what I'm going to do is create a plane, and I'm going to base it off my origin work planes as we discussed already. So I'm going to offset it from there, and I'm going to name this parameter as well, and it's going to be my outlet height. And I'm going to put that equal to 800. And I'm going to create a sketch on top of that plane and project the geometry from my first sketch. And what I could do as I go along is rename my work plane and call this outlet height. So if I do want to change things, I know what work features are dictating certain things. So last one, just to finish off the geometry, is I'll project it again from the XY plane. Click and drag up. And this is going to be my chute height. And I'm going to make that maybe 1500. And again, I can name my work plane as I go along. Whoops. And call that chute height. Then I'll just put a sketch on this last work plane and do the same thing as what I did earlier. Put on a rectangle and I'll name the dimensions as I go. And this time I'm going to call it my inlet width equals maybe 1000. And my inlet depth equals 800. Okay, so again I'll just constrain that sketch very quickly. And again I'm working off the center points and planes and so on, as you see there. So finishing that sketch, what I'm going to do is just turn off the planes visibility, so we can see the three sketches that I'm working with. So from here what I'm going to do is create a loft, and I'm going to use a surface loft. So I'm going to create first of all a surface loft for the inlet, or the outlet I should say. Click OK. And I'm going to make my sketch 2 visible again, so I can continue and make another loft from the top sketch. Again, it's going to be a surface loft. Top sketch, and I'm just going to have to join, thought I had to join the dots, but I picked up the loop there nicely and click OK. So what I've got now is a surface. Okay, and this surface will allow me to position sketches nicely when I start deriving this part into other parts to create my assembly. So I'm going to hit save, and the rule in modeling and designing and drafting is save early and save often. And I'm going to call this master sketch chute. And before I move on to the next parts, what I'm going to do as well is I'm going to go into my parameter table editor, and I'm going to create some user parameters. So by going up to my quick access toolbar, I can click on the little FX symbol again, and that will open up my parameter table for me. So I can add numeric, and what I'm going to do is I'm going to create a parameter that's a user parameter and call it flange length. And I don't need to open vault at the moment. And I can make my flange length, let's say 250 mil. Okay, so that parameter doesn't control anything yet. And I'm going to do the same thing, just add another numeric parameter, and I'm going to call it assembly thickness. And you'll notice I'm not putting any spaces in my parameters, and I could just use an underscore if I wanted to spread the words out a little and make them a bit clearer. And I'm going to make my assembly thickness, because it's going to be a sheet metal assembly, I'm going to make it 10 mil. Well, let's make it 5 mil to start with, and say done. But before I actually close the parameter table, what I'm going to do is I'm going to tick both of these user parameters for export. So on the column export parameter, I can put a tick beside these two, and that means those parameters will be marked when I start creating derived parts as parameters to export. So I'll click done. And what I'm going to do now is start creating the individual parts for my assembly. So previously, to derive a part, what you would have to do is open a new part and then finish the sketch, go to the Manage tab and say Derive Part. But there's a nice little productivity enhancer in 2014. I think it got added in 2012 actually. So if we go to the Manage tab, you've got the option here on the Layout panel to make a part. Okay? And this will actually derive a part from the part I'm working on. So it spares a bit of time. So I'm going to call this first part, and I'm going to just call it left section. I can pick the template that I want to use, which is going to be a sheet metal template. I'm not going to place the part into a target assembly, because I just want to work on one part. I'm going to tell Inventor that I want to include surface 1. Just click OK to that, and surface 2, as well as my user parameters, which have been marked here for export. You can see the little symbol beside them. And I'm going to bring in my flange length and my assembly thickness. I'm going to click OK, and that should open up a new part, which it does. And we'll go to our home view. So you can see it's derived in the two surfaces that we want to work with. So this is going to be my left section, so this side here. What I'm going to do is I'm going to click on Create 2D Sketch. And I'm going to create a sketch on the first phase. And you'll notice that I have Auto Project Edges during sketch creation turned on. So the edges are projected. If that's not turned on, what you can do is you can go to the Manage tab, Tools tab, Application Options, go to the Sketch tab, and there's an option here to turn on Auto Project Edges for sketch creation and edit. So you can toggle that on and off if you want your edges projected. Normally I have it turned off, but if you do want to turn it on, in this case when it suits you, you can turn it on. So I'll repeat the last command, create a sketch again, and pick the top face. Oops, create 2D sketch on top of that face, such that the edges are projected again. Okay, so now we've got two projected faces. Let's finish our sketch and create a face. And I'm just going to make sure by zooming around that it's offset in the right direction, so outwards, which is good. Apply, and I'll offset it again in the correct direction, and OK. So you'll notice it uses the default thickness, which isn't what I want to use. So I'm going to go to my sheet metal defaults and tell it not to use thickness from rule, and instead show me the parameters that are available to it. And you can see the very first parameter in there is assembly thickness. So that's the parameter I exported from my master part. And you'd see you need to take out the numbers that are in the thickness option box first. Otherwise you get a big red indication, and red means Inventor doesn't accept it. So we'll click OK, and our thickness has changed. If we want to do a quick check, we'll go to Measure, and our thickness is now 5 mil. So I just change my view as well to show shaded with edges so we can get clearer definition. Okay, so we've created one part. Now let's put a flange on there, and go back to our sheet metal. We'll say flange, put it onto the end part here, and what we're going to do is, instead of accepting the defaults, we're going to again list parameters, and you can see flange length appears there, and it calls up that flange length from our very first master part. So that's in essence, that's the procedure for creating parts derived off another part. So what I'm going to do is I'm going to save that. And I'm going to repeat the same process just for the other remaining sides. And that way then we'll actually see exactly how it's been created and give people a chance to kind of really understand what's going on with the master sketching side of things. So again, make part, put on surface 1, surface 2. This time I'm going to call it the bottom side. I'm going to use my sheet metal part again, not placed in an assembly, and bring the same two parameters over with me. And again, this creates the bottom section. Let's give a look at our home view. And what I'll do very quickly is create my sketches here, finish sketch. I'm pressing spacebar on my keyboard to repeat the last command. Which will just speed things up in the creation. And again, sheet metal defaults, take off use thickness from rule. And let's make it assembly thickness. And let's put a flange on there. And when I drop down, we'll see flange length is already in there. So very quickly we can create more parts. So going back to my master, I've done the left, I've done the bottom. So let's rotate around and do the right. So again, make part, right section. You don't need to place in a target assembly, sheet metal part. Bring the surface bodies that I want to bring across. I could bring sketches if I wanted as well. So it doesn't necessarily need to be a surface, could be a solid as well. And let's bring these two user parameters across as well. And let's go to our home view. And let's do the right section. Create face, right click, finish sketch, spacebar to repeat the last command, put on a face, change our sheet metal defaults to read the parameter that we want to read, and put on a flange, again, which is distance, flange length. Okay, so I can save that and complete the last section. Back to our master sketch, and the last section is the top. So I'll make a part from that, call it top section. Pick the surfaces I want. Again, sheet metal part, and don't need a target assembly. So a target assembly was if you're updating an existing part. Okay. So let's look at our parameters and bring our flange length and assembly thickness in there. And I've just noticed someone has asked a question. And if I see a question that I can answer quite quickly, I will do that. Otherwise, I'll leave it till the end. So someone has asked the question, why change flange length and material thickness using parameters and not the options available in sheet metal? So the reasons that I want to bring in the parameters for flange length and assembly thickness is that when I want to change my thickness or my flange length, instead of going through all the individual sheet metal parts, I can just go to my master part, make one change there in the parameter table, and then it'll update all 4 sections. So you'll see this in a second. So let's continue on, and our top section, okay. Give a look at our home view, and again, let's give a look at the top side, and we'll just repeat the same procedure. So create 2D sketch, finish, new sketch, finish, face, make sure it's going in the right direction, and just check the direction again, and okay. Sheet metal defaults, and as I was saying, I don't want to use the one in each individual part. I want to use the one that's controlled from a master part. Assembly thickness, and put on a flange. And our flange is going to be flange length. So saving that, we can now create an assembly file. So let's go to our new and create an assembly file, standard assembly. I'm going to right click and say place component. And I'm going to bring in my master sketch part, and I'm going to bring in my top section, right section, bottom section, left section. So these are all the parts that I've worked with. Click open, just zoom out, and as you'll see there, each part has got the surfaces turned on. So to make things tidy, what I'm going to do is going to go back, and this is best practices as well. In each individual part, you'll see that when I expand the item in the browser tree called master sketch shoot.ipt, and this is my derived part. So do you remember in the presentation I said these techniques use derived parts? So what happened was we created a derived part of our master sketch into the part left section, and we derived in our surfaces and our parameters. So I'm just going to turn off the surfaces here in each one and save them as I go along. So it'll make it a little bit tidier when we get to the assembly level. And that's a good idea, keep things tidy, makes it easier to work. Okay, and the top section, let's turn off our surfaces. So when we go back into assembly 1, we've got a nice clean workspace where we've got our master part, which is the surface model here. And we've got 1, 2, 3, 4 different sections. So best practices when you're working with top-down design techniques. Bring in your master part always into the assembly, and be sure and turn it into a reference part, and we do that by going to our bill of materials, because we don't want to have our master part turning up in our bill of materials or our parts lists. So master sketch, we change that to reference, so we won't see it in our parts lists and our drawings. The next step in this procedure is we go to our productivity panel, which is on our assemble tab, productivity panel here, and we want to use ground and root component. So each of these parts, I'm going to tell Inventor to ground it and route it to its XYZ. Okay, because all these parts share the same XYZ, and they'll all be orientated in the same position. So pressing space bar on the keyboard, I can repeat the last command, and each of those sections are grounded and routed to the XYZ. So what I'll do is I'll just turn off my visibility of my master sketch. And again, best practice is always leave your master parts up at the top of the browser tree. The reason for that is if someone opens up the assembly, they know straight away that this part hasn't been created in the traditional bottom-up design technique, and they may think, why the hell is everything grounded? But by putting in your master part, your master sketch, onto the top of the browser tree, it indicates that this part was created using a top-down design technique, and it's being controlled using a master sketch. So, okay, so I've built my chute assembly. Now I realize that, hold on a second, my flange length, it looks a little bit too long. So to make a change, all I need to do is go back to my master sketch part, go to my parameter table, change the flange thickness and our flange length and make it 100. Click done. Can update the master part, go to my assembly, hit update up in the top left hand side, and all 4 parts change. So that's the reason why I didn't use the flange length and the material thickness within the sheet metal parts, because I can make changes to multiple parts in one go by using the master sketch technique. So for example, we go back to our master sketch, and let's say design changes have come in. So design changes calls up. We want to change our inlet width to 1500, our inlet depth maybe to 600, chute height 1200, outlet height 900, outlet depth and outlet width, we can change those as well if we like, 500, make it 350. This will probably look a funny proportion. And we want to change our assembly thickness to 6 mil thick. So done. Update, and you can see the shape of my surface model, but maybe that's what the client wants. So let's go to our shoot assembly and update it. And you can see our model has flexed and changed and updated. So you can see I drastically changed the shape and the dimensions that I used and all the parameters. So that's why I mentioned at the start that the key thing is having a think about how you're going to model your design and defining the key parameters that will change, and then using an intelligent design technique like master sketching and creating user parameters to design your part. So you can see there in the changes that if I were to do individually, I'd have to go back and change single parts, and it would take a lot longer. So you kind of have to ask yourself, is it worth putting in that little bit of extra time at the start to create a top-down design technique, which will save you time later on when you need to make changes? Okay, so that's master sketching. The next technique that I wanted to show everyone is solid body modeling. And for this one, rather than repeating things we've done already, I'm going to open up this solid body modeling part, and it's got a sketch created on it. So in this case, I'm going to try and create a pressure vessel. And basically, I've just got 3 concentric circles put onto this sketch. And what I've done is, as I put in the dimensions, I named the parameter. So this dimension is called ID. That's 120 mil. ID for inner diameter. This one here is a dimension that's based on the ID and the OD. So when you're using parameters, you can work it a little bit like Excel, and you can put equations in there. So you'd see my dimension here, which is called PCD, for pitch circle diameter, for my bolt circle. It's equal to my inner diameter plus my outer diameter minus my inner diameter divided by 2. So if I change my inner diameter, let's change it to 60, my OD comes in, and my pitch circle diameter for my bolt holes comes in as well. So I can change that back out, and everything is related to each other. So if I go to my outer diameter, I've told Inventor that my outer diameter is equal to my inner diameter plus 30 mil. So if I right-click and I go Dimension Display and Value, Dimension Display and Name. It changes and shows us the names of each of those dimensions, and when we click on them, we can see what formulas have been used in them. And that's the same then with our parameter table. It's up here. And you can see that the equations are just popped in here. Okay, so with solid body modeling, I've created my sketch that I want to create my geometry with. Then I go to Extrude, and I'm going to create a part here, so a base. I'm going to say OK, make it 10 mil. And then I'm going to go to my sketch. I'm going to turn on the visibility. And I'm going to create a new sketch up on the top. Then I'll project my geometry for my wall thickness onto that sketch. Finish it, extrude. And what I can do here is I can select join, which will join the part, or join my 2 extrusions. And I can give this a name as well. So you can also name features. So height equals, let's just make it equal to the OD. So if I want to pick up a parameter, I just type in the name of the parameter, and it's going to be equal to the OD. Okay. So all we've got is we've just got a simple extrusion like it create a normal part. So the next step we'll do is going to create a second part. We'll create a 2D sketch. And again, I have my project edges turned on. And this is the gasket I'm going to create. So finish sketch. And I'm going to create an extrusion. I'm going to make it just 10 mil. And instead of clicking on join, as I did previously, what I'm going to click on is the button that's below here, and it's called New Solid. So I click on New Solid, and then click OK. So what that does is, Again, I just need to change my view. You can see that we've got two solids created in our part environment. So if we go over to the left-hand side, we've got solid bodies folder, and we've got solid 4 and solid 5. And I can name these solids as I go. I can say solid 4 is going to be the base. Solid 5 is going to be my gasket. And if I wanted to even further differentiate them, I can go to the properties, and I can change the color. Okay? So very clear and easy to see the different solids that I'm working with. So I'll repeat the last step again. So I'm finishing the sketch for the cap. Extrude, and I press my solid option here. And it's going to be a new solid. I'm going to pick up on both profiles, and again I'll leave it 10 mil cap. Click OK. And you can see that a solid body has been added over on the left-hand side. I'll just call this top. Okay, so if I want to put some features on here, for example, let's create another sketch and project the circle called PCD onto that sketch. And I'm going to put on a point to put in some bolt holes. So if we're putting in features like holes, we can say centers. Yes. We can click on the solids button over here, and we can tell Inventor we want the hole to go through the solids. So you have to pick the solids you want the hole to go through. So you got 1, 2, 3 solids selected. And then I can put in the geometry for my hole. So perhaps I want to countersunk hole. And what I'll do is I'll just click and drag. Put it in approximately. And increase the depth of it. Oops. I think I might have dragged the wrong side there. Okay, so we'll click OK at that and give a look at the hole. So counterbore, yeah, it's dragging on the wrong arrow. Counterbore should be that depth. And click OK. Oh, I'll try that once more. Cancel the hole, and let's drag down the depth. Ooh. Okay, I'll just punch in the numbers rather than trying to do it graphically. It'll be easier. So let's put in a threaded hole, and let's put metric M10 should be right. And yeah, we can. Let's see the counterbore. 5.5, which wouldn't be right for an M10. So let's make that 13. That looks about right, and the preview is coming in, which makes sense. So the numbers I had in previously were not sensible. And let's make that fully threaded down, so 38. And we click OK. So okay, we've put in a whole feature in there into our solid body. The key thing was when we're putting in features, we had to click the hole or the solid option and pick the solids we want the feature to go through. So if we want to pattern that hole, we can use the circular pattern. We can pick up on the hole feature, tell Inventor the rotation axis we want to go around. And you'd see what we've got up here is we have the option to pattern solids or features. This time I'm patterning a feature because the hole is a feature. I can tell Inventor the rotation axis, click OK. And you can see we've got holes put into our top solid. So the thing to watch out for here is when we're using patterns with solids, we actually need to do it for each solid. Okay? So you see the pattern, and then I need to tell Inventor, okay, I'm putting the hole through the gasket this time, and click OK. And repeat it again just once more for the base. Same rotation axis, and then just telling Inventor that the solid is different each time. And that way the pattern goes through each of those 3 solids, because it doesn't allow me multi-select solids. Okay, so that's my assembly created. What I could do next is if I want to put in another hole, let's just make it look a bit sensible. And put in concentric on this surface, this axis, and yeah, we can accept the same depth. Okay, so that's our assembly created in our master part. So now what we do is we go to our Manage tab, and we click on Make Components, and we tell Inventor that we want to make components from the base, the gasket, and the top. We can pick the assembly template we want. We can pick its location here. Put it into the same folder. Next, and we can pick the part template as well if we wanted. We could change it if we liked. I'm just going to accept the defaults. And what we've got then is we've got an assembly created. And we're in the assembly environment with each of our 3 parts. And each of the parts are grounded automatically. So it's like, in a way it's similar to master sketching, but you don't have to derive each part individually. So if we go back to our Make Changes, to our solid body part, which in this case is our master part, we just need to go back to our initial sketch. We can use our parameters, or we can use our parameter table if we wanted. Let's say our ID is going to change. We're going to make it 200 mil. Say done. That updates our sketch. Finish our sketch, which updates our part. When we get out of the part, we can go back to our assembly, hit the update button on the top left-hand side, and our assembly updates. So again, very quick way of changing an assembly. So spares a lot of time. And as I said, best practices, let's place in our master part, which is our solid body modeling part, and we'll place that into our assembly. We'll right-click, we'll OK. We'll ground and root it so that it doesn't get in the way. And we'll turn off its visibility. And again, don't forget to go to your bill of materials and tell Inventor that your solid body modeling part is only a reference part. That way it doesn't show up in your parts list. Okay, so that's solid body modeling in a nutshell. Let's give a look at the last technique, which is layout design. And as I said earlier on, this is for designing mechanisms mainly. So what I've done is I've created a part already, and I've sketched in some shapes. I've put dimensions on those sketches, and that's about it. So I just sketched in the shapes, nothing fancy about it. And that's what we're looking at the moment. So what I do is I select the shape that I want to make a block out of. I go up to my layout panel and I click on Create Block, and I give it a name. I can call this Link 1 and click Apply. And I can do that for all the different shapes that I've created. This is going to be my mount. Click Apply. And as I'm doing this, you'll see up on the left-hand side here, we've got a folder called Blocks being created. When I expand that, you've got Link 1 and Mount in there being created. And I'm just going to create a simple slider mechanism. So that's going to be a slider, and this last one up here is going to be Link 2. Very creative names. Okay, so let's use our constraints panel up here to position our sketch blocks. And you'll notice that our sketch blocks, the dimensions disappear once I create a block. If I want to edit the block, I just double click on it, and I'm into the sketch mode again. If I wanted to add different components, I can go over to the left-hand side of the screen, click on the block that I want, and click and drag it in. So it makes it very easy for recreating certain shapes. So I don't need those, so I'm just going to delete them. And I can start positioning the components of my sketch block using constraints. So I'm going to put a coincident constraint. Again, I'm working off the center points. And using the coincident constraint, I'm going to join these sketch blocks together. Okay, I'm going to use a horizontal constraint. Tell Inventor that this point has to be horizontal with this point, and this line also needs to be horizontal. So what I can do then is I can click on my sketch block and I can design my mechanism the way I need to. And dimension it, create it, and modify it exactly the way I need to without having to create an assembly. So I design everything at the sketch level. Once I'm happy with that, I go to my Manage tab again, and I say to Inventor, this time make components, and we'll work with Link 1, Mount, Slider, and Link 2 by clicking on the blocks over on the left-hand side. I'll use again the standard template, It's going into my folder that I'm working on. Click Next. I can use my standard templates, or I could change them if I liked. Click OK. And again, we're in our assembly environment with parts created out of each block. So, to convert these blocks into parts, what I do is I double-click on the part, click on Extrude, and I can start extruding thicknesses to these parts. So let's extrude that again. Let's go the opposite direction, 10 mil. Return, and extrude this section out. Return back again, and finally the block. And the quick access toolbar, you see there when I click on a line, it comes up with the extrude option, which is really handy. So, whoops, I think I've extruded that in the wrong direction. So let's go back and, I think there's a little bit of interference in the directions, so I'd need to go back and modify that if I have started extruding in the wrong direction. But I think you get the idea of what I was trying to do. And you can see you can actually extrude the parts that we're working with. So that's layout design in a nutshell. Again, I'd probably have to modify this slider block to just accommodate this link here. But the same idea applies. It's used derived parts in this layout part. And we've created a mechanism from initially working with 2D geometry, which is quite useful. We can do that quite quickly. Design our angles, design our lengths, design our clearances. And then we know everything's going to work. So we don't have to spend a lot of time creating an assembly and then changing constraints, modifying constraints, and changing angles and so on and so forth. So there are 3 very useful advanced design techniques for Inventor. So let's jump back into our PowerPoint and quickly review the 3 different techniques that we covered. So master sketching, which is commonly referred to as skeletal modeling, is very useful for large structures. People often use it for pressure vessel design, large sheet metal structures. Layout design typically is used for mechanisms, moving components. Solid body modeling. I've seen solid body modeling used pretty much for everything. Some guys will tell you it's better for consumer goods and plastics, which it can be used for, but I've also seen guys create very, very large assemblies using solid body modeling. So the question you ask yourself is, what sort of changes you want to make to your assembly? And that will dictate which technique that you need to use. So in my opinion, the ones I see used the most is solid body modeling and master sketching. So they're typically used over and over again by lots and lots of people. So what I'll do is I'll leave some time just for guys to punch in more questions. And if you wanted to go back and see what the step-by-step techniques are covered in this webinar, you can go onto our website and there's an archive for all the webinars. We also have a YouTube channel, which is quite good. So you can get on there, you can log on, and no, you don't even need to log on. I think it's open to everyone. And you can view the webinar again. You can have a go at master sketching, have a go at solid body modeling and layout design, and see how it fits into your design process. See if it's going to be something that's going to increase your time and make designing and changing things a lot easier. So there's some questions that come in there. And Elliot has asked, how do you offset the part from your master sketch once extruded in an assembly? So how do you offset the part from your master sketch once extruded in an assembly? So you want to offset the part at the master sketch level, I guess. So the only way you do that is by offsetting your planes. So changing your planes and changing where your sketches are. So I think that's what you're asking. This is, if I go back to my master sketch here, and if you wanted to change an offset here, what you'd actually have to do is change the position of where that surface is. So in here, if you wanted to offset that differently, So the options you have here from the way I've created it are modifying your dimensions, which in turn modify the assembly. But if you wanted to offset the part from your master sketch once extruded in assembly. So, okay, if you wanted to change that without having to go back and change your master sketch, what I could do is I can just right-click on any part and take off the grounded option, and then I can reposition that. So let's get rid of these constraints. And I can reposition and move that part if I wanted. So if you wanted to do it quickly and easy, you could just change it. That part is still referencing my master sketch, but all I've done is said, look, at the assembly level, you don't need to reference the master sketch, because the only way it's referencing the master sketch at the assembly level is, it isn't really, it's just grounding and routing the component. So both systems, or both parts have the same X, Y, Z. So two options you have. One is going back to your master sketch, offsetting the plane or changing the dimension of the plane or the parameter of the plane, or creating a new sketch and then creating a new part from it. Or you can go to the assembly and just change the constraints. So I hope that answers that question, and I'll leave another minute or so for people if they want to think of any other questions. And hopefully I'll try and answer them. Okay, so looks like people are happy enough with what they've seen, and there's no more questions coming through. Okay, so thanks very much for your time, guys. Okay, so one more question. Can you create that sheet metal chute as one part and rip it? Yeah, so if I wanted to create it as a part and rip it, I could, for sure. But perhaps we wanted that to be just one very, very large piece of sheet metal. So, for example, if we go back here and my dimensions start getting pretty big, so we'll go back and we'll look at our outlet sketch, and let's say, let's change maybe our outlet. So we'll go to our outlet, make it quite big, outlet width, or inlet I should say. So inlet depth, maybe make that 1500 as well. Done. Update. Go back to our chute assembly. Update. And you'll see there that our chute is getting quite big. So you could create it as a single part and create cuts. It would be a pretty weird flat pattern. But I guess the question is, can you find a sheet big enough as well? So yeah, for sure, you could create it as one sheet, but I'm not too sure how the flat pattern would look, and create a rip. So that's an option for lofted shapes and so on. So yeah, that's definitely an option. But the case is, can you get someone to cut that flat pattern, and can you get a sheet big enough for it? So the example I looked at was creating 4 individual parts. So if you can create a flat pattern from one piece, then I guess that would be the way to go. Okay, so let's okay, so Anthony has asked how often do we do webinars. So at the moment we're pretty much doing 1 or 2 a month. So if you've got any special requests, just send through an email, and I'll give a look at it. So what I'll do is, as people are asking that question, I'll very quickly give out my email address. Oops, that. So if you've got any specific suggestions, or you'd like to contact us to find out more about things, I'll just increase this font to make it a little bit bigger so people can see it. That's my email address. So if people want to contact me and ask me about or provide suggestions for different webinar topics. More than happy to take on any advice or constructive criticisms as well. If you want to make any suggestions on how we could do this better, feedback is very important. Or if you want to contact our sales guys or anything, you've got the general telephone number, which is down here on the bottom of our screen, 1800-223-562. Get in contact with us and let us know. But, yeah, our webinars are held pretty much every month or even twice a month, depending on what's happening. So thanks very much for your time, guys. I appreciate it. Appreciate taking time out of your busy day to watch this. And we'll see you next time, hopefully. Okay?